Hello and welcome to this webinar. Thank you all for joining us. My name is Stuart Scott and I'm from Cloud Academy, and today we should be discussing distributed tracing and its implementation with microservices and containers within the cloud. Now, hopefully this will be valuable to a lot of people, as organizations are now see the advantages of developing applications and solutions utilizing microservices instead of the monolithic applications implemented in the past. Now, using microservices allows your architecture to operate independently of other components. And this allows each service being utilized to be updated, deployed, and also scaled as and when the demand requires it to do so. Now, these microservices architectures can become complex with multiple components all playing their own part. But how can you monitor and identify issues and incidents quickly and accurately with so many parts involved? And this is where distributed tracing comes in. So looking at the agenda for today, we should be covering the fundamentals of distributed tracing using open tracing. We'll look at instrumentation and trace collection, and also perform a live demonstration as well. Now, on the panel with me here today, I have the CTO of Epsagon and Ribenzaft, and also Peretz, a software engineer also from Epsagon. So thank you both for joining me today.
Thank you.
It's a pleasure, thank you. Now, this is not the first webinar we've done together, and looking at the success of our previous webinar, I'm very much looking forward to what you guys have prepared for us today. But before I hand it over to you both, I just want to let everyone know on the call that if you have any questions throughout the webinar, then please post them in the chat window and we'll have a Q&A session at the end, and we'll try and answer as many of them as we can. Okay, so let's get started. Over to you guys.
Perfect. So again, thank you very much for having us. It's a pleasure. So let's talk about technical stuff. We're here for distributed tracing. Let's start with the basic and the foremost thing. What is distributed tracing? I think we covered some of this in our previous webinar, but just to align everyone up. So a trace tells a story of a request as it propagates through our system, our application. In one example that we see on the left-hand side, we can see a client calling our load balancer, which interacts with 3 different services. And a distributed trace, honestly, what it tells us is what the request is doing in each and every resource. So we can track down what went on the load balancer, and then in the off service and the billing service and some other resources that we have. It's really crucial, and we will understand really now why it's so important to have this kind of distributed tracing. Now, when I'm talking about system or distributed system, we mainly refer to distributed applications. And one example that we're seeing on the left-hand side is distributed application fundamentally composed with multiple compute parts. It can be containers, serverless, any kind of resource or framework that you're running. And when it becomes distributed, so there are messages that going from one service to another. So it can be either through a message queue like Kafka or SNS. It can be on an HTTP messages or RPC messages. It can be also via third-party APIs like Twilio or Stripe. And all of these components are composing our application that can be in production. And without the ability to know what's going on from one end to another, it's almost like we're blindfolded to our own application that we built. On top of that, if we're looking about the modern cloud of applications, the one that are built on cloud and using more and more managed resources, sometimes we don't even have access to the underlying host or the infrastructure itself. So there it's really become crucial to know what's going on, because no one is going to tell me what's the CPU metrics for an SNS, or I know how much memory my S3 is consuming. I need to make sure that it's working properly. Why do we need this distributed tracing? So on the left-hand side, again, we see an example with and without distributed tracing. Let's say, for example, that I got a user complaining about my retail website that he haven't got any confirmation email. So I might be able to track down if my latest service is responsible for sending the confirmation email or something like that. I'll be able maybe to track that service. But then I want to move backwards to do a real root cause analysis. And I can't go backwards because I don't know any relation between the horizontally scaled service to where it was talking to, or how, or via which resources. So it's almost hard to track down from the beginning where the user started. Where when we got distributed tracing in this example, I exactly know based on a single parameter the trace or the path of the request as it propagates through every service that I got. It can be the billing service and the confirmation mailing services and so on. So the first and foremost thing is to be able to track requests from one end to another with easily and efficiently. The second thing is to detect performance bottlenecks. Let's say another customer is making a purchase, but then he receives the email after, 30 minutes, which is not applicable. I mean, nobody wants to wait 30 minutes, or let's say even few minutes to get an email confirmation. It should be, let's say, few seconds at most. With distributed tracing from one end to another, I can easily know where am I spending my time, whether it's the API gateway that is serving the slowest performance, or my mailing service, or something in between, any processing in between. It can be data pipelines or just backends. I'll be able to pinpoint each and every request along the way of how long it takes. So let's talk about first step in distributed tracing. So far it was some sort of introductory. Now let's dive into the main items that we will cover. Let's start first with open tracing. So open tracing is probably the widely adopted API and framework that defines how to capture distributed traces. It tells us how to capture an event. Event can be I'm putting something to a database, I'm getting a request on HTTP, I'm processing something, I'm doing something, and each kind of this event is a span. This is like the terminology in open tracing. Every span we can attach a context to. A context tells us a bit more about the span. The span just tells us, okay, this operation took place and this amount of time, but sometimes I want further information. For example, if I'm interacting with AWS resources, I might attach a key value pairing of region and the exact region that I'm running on.
So you can investigate and understand, while you investigate, you can understand more about what the event really did.
Exactly, give me context for every span. Now, spans are related to one another via two ways. It can be either a child of or follows from. We'll soon show an example of how exactly it looks like, but it means honestly that once we have a span and a following span, it can be either a child of this span, like something that in the context, in the process of the same thing, or follows from where I'm just pushing something somewhere, usually asynchronously, and then somebody takes care for it. The last thing that we need to make sure that we know about open tracing is the inject and extract. So to be able to correlate between different traces with different processes and different environments, we should inject, every time we go outbound of our process, we should inject some ID that we generate and we're responsible for. And on the other side, we need to extract it. So we will know that we're not a new span, we're not the root span, we're continuing a part of something else. Let's show an example of a span. I gave an example in Python. Most of our examples in this session will be in Python. So Django is probably the most popular web framework for Python. And let's say I'm getting a request. This is my root span, the one that, okay, I'm handling a request now. Now I've got two spans underneath it, which in a child of relation. Every time we go down a layer, it means that it's a child of. So these are internal things that I'm doing in Django. One of them is a sub-process that getting from Redis some information in the cache that I need for the further code. And then the second one is storing something to a database, which also a child of, a PostgreSDB. And then calling another resource in Python, just regardless of the Django, just invoking some Python code, which publish a message to Apache Kafka, and then it calls another service that consumes this message. This example, by the way, is follows from. It means that this part, from that moment on where it reaches the Kafka topic, it's no longer part of this root span. It's not the same tree anymore. It's starting a different tree, but it follows from the same tree.
So it's mostly used for asynchronous.
Exactly. Any async kind of events that I'm finished with handling it and I'm passing it to somebody else, this is exactly the use case. Now, regarding injecting and extracting the IDs, so in this example, let's say we have a Django application, again, web framework, I'm getting a request. Since I'm the root span, I'm creating a trace ID, let's call it X, with a span Y, this is the Django that I'm running it. Now, to be able to track it through a Kafka message, Kafka topic, I need to inject into that Kafka some header that will propagate to the next span context. So I'm injecting this kind of ID that I'm generating, this X ID. And on the other side, when I'm consuming this message, I'm gonna let the new span that is starting in my other server to say, okay, do I got any extraction of a trace ID? In this case, yes, I'm getting this X. So I know I'm part of a bigger trace, something that started before me. And I'm generating a new span ID for me. So this is a uniquely span for me. So this is an example of how to trace down from one end to another using the inject and extract. Now let's talk about collecting spans and context for incoming requests. So we showed just the general guidelines about how everything looks, but now we need to implement such things. So let's say I've got a Spring Web application or Django or Express. These are probably, you're familiar with either one of them or all of them. Now, for every time that I'm getting a request, I need to run the following operations to start using this open tracing. Now, before request, let's assume I'm getting the request and some tracer that already initialized. First thing I need to do is to extract the trace ID. I mean, to know whether I'm the root span or there's somebody else that already called me. I'm doing it from the headers. Then I'm starting a span which says, okay, now I'm starting to take care for my own requests. And then I can set tags. Tags are the exact context that we talked about. For example, I want to know what is the URL that I'm taking care of in this exact request, or the remote IP, if I'll need to investigate who called me, or the caller name, or the remote port. Any kind of this information is the exact context that we talked about that will give us some vital information when we're troubleshooting anything. Then comes the part of tracking not only incoming requests, but also outbound requests. So let's say in my Express application or Django application, I'm calling a third-party API, let's say Stripe, for charging my users. So every time I'll make an outbound HTTP request, there's also need to be a before and after, but let's talk about the before. So I need to do some things. First, I need to call my global tracer to know which part of my running am I, and start a new span that says, okay, this is the event of charging a user in Stripe.
This is similar to the part you demonstrated before.
Exactly.
You need to extract the you've been before.
Exactly, and here I'm covering some similar information like HTTP, the URL, and the service name, and peer service and peer port, things that will allow me to investigate further on. And then we need to remind ourselves that we still need to use the inject, because in this case it's Stripe and we're not monitoring Stripe internally. But if it was any other of our own services that we still want to monitor, we need to inject our trace ID, so then afterwards somebody would be able to extract it. So it means that just to capture, some basic stuff, there is a lot of code that is running over here, and we just need to, collect all of the details.
Just a note to our people that see this, if this seems a bit overwhelming, right after run, I'm gonna go through a live demo about step by step how we exactly can do it. So yeah, don't worry.
Yeah. And as I mentioned, it doesn't end. I mean, we're using not only HTTP resources, we're using databases and storages and message queues, and some of them are managed ones. And we need to think about everything. We need now to instrument, or let's call it adapt or code every request that we're doing before and after. And these are just a small example of resources that we're using. And honestly, injecting IDs, in some cases it's okay, like the header of HTTP. But then if I want to trace down something in a Kinesis or an S3 object in a bucket, so it's turning to be a bit hard to inject this kind of IDs because there is nowhere. I can't do it. I can't inject into the file name something else because it's very intrusive. And also, we collected some context, but what about more context? I mean, maybe I want to see the payload, or maybe I want to see some more information that is meaningful for me. So what, now I need to capture everything? And what about logs as well? I mean, we haven't talked at all about the logs that we need when we're investigating some problem. And it leads me to the part that it requires a lot of heavy lifting just to get up and running with tracing, distributed tracing in production. And obviously it requires constant maintenance over the time because we're changing services and we're adding things, and our application is dynamic. And only if somebody could automate this process completely so we don't need as an engineers to take care for it. Luckily there is. So let's introduce instrumentation. Instrumentation refers to the task of including another code on top of our existing program. Mainly in computer science, it's mainly tied to detecting performance or track any operation. So in our case, performance monitoring and troubleshooting, and exactly what we're looking for in here. It acts like a wrapper. So in some extent, it's like monkey patching, but more advanced way, like we're doing in unit testing to mimic some operation and change the behavior, the original behavior. And once we're changing the original behavior, it allows us to capture any kind of events automatically without us needing to do before every request and after every request. This is super easy on high-level programming language like Python and Node. It's a bit harder on compiled languages, at least if you're trying to do this in a seamless way of something that integrates to your code rather than you're coding all of this. Let's give an example in Python. So let's say I want to instrument each and every Redis call that I'm making. So in this example, I'll have to wrap my function every time that I'm calling the Redis library and the Redis class.execute command. Instead of telling Python go to this function, I'm telling Python to go to this function, the Redis wrapper, which presented right over here. This I'm doing just one time. It's a one-time patching that changes the address in the memory of this specific operation. Now, every time it will be called, I'll get to here. So somebody did this automation for me of instrumenting each and every Redis request. From that point, I can capture anything that I want to. Let's say I've got a class that I'm collecting some information. So I'm collecting the data about the operation, about the key that I'm putting or doing something to Redis, and when it happened. So it's much easier. I mean, I'm just defining it once, and for every operation, this wrapper will be called.
So you can share this code with your team. So
exactly, everyone benefits from me doing one thing rather than I'm doing myself before every request. Now, we talked about collecting traces, but what about showing them? We need to visualize them in a way that is meaningful for us, in a way that we will be able to explore the data. And I think Jaeger tracing is probably the most popular one for showing traces. There are some other alternatives that we will show, but this probably is the most popular one. And the view here is pretty straightforward. This is a Jaeger example of a front-end application going to back-end and using some Redis. We can easily detect here where our request is spending most of the time. So it's going from one resource to another. We see all these Redis requests. We see how long they take. We know how to pinpoint and troubleshoot bottlenecks because we know, for example, which Redis operation took the most time, or even where do we got problems. Like we can get like bad signs from Redis if we're not doing something properly. And then also to trace down the request along the way from each and every call to another. So it's pretty easy to discover and understand this kind of operations. Now, these examples that we show with both Open Tracing and Jaeger are not the only one. There is OpenCensus, which is also an open source set of libraries. It mainly defines or allows you to collect easily application metrics for distributed tracing mainly. So you can read about it, but let me jump to the second part where actually Open Tracing and OpenCensus merge together into Open Telemetry. So this is the new standard of both tracing and instrumenting and collecting the traces and aggregating them all together.
Sorry, just want to jump in here just with a quick question. So what if I wanted to implement this tracing engine for my team at high scale? What should I do?
Right, that's a great question because just collecting the information, I think I might say that is the easy part, but now I'm ingesting tons of traces. So Jaeger will be able to ingest them, but if I'm talking about really tons of information, billions of requests, hundreds of billions of requests, and traces that are coming in, I need something much more scalable. I need to, it's either build my own thing, like build my own super scalable Jaeger with maybe some Elastic to be able to query some data, or to use something existing. There are some providers that provide, let's call it distributed tracing as a service that allows you to send traces, or even they generate the traces for themselves. One of them is obviously Epsagon that we will discuss afterwards. But anyways, it's not an easy task. It's really takes some time and efforts to lift it from nothing. Regarding another alternative to Jaeger, there is Zipkin or OpenZipkin, which is also a distributed tracing system that you can throw traces at and it will parse it to you. Now, I think that I talked too much about the theoretical part, and I'll let Chen come in and maybe talk about like the real stuff and how to implement an example with distributed tracing.
So I think I just want to take all this point in the presentation, take all the theoretical thing you said and try to really do it, and hopefully things won't crash during what I do, but at least anyone can like learn from it. So let's start. So what is our goal? We want to be able to build a distributed system, and we want to take that system and start sending traces from each of the services. And those traces need to be sent somewhere. So obviously we also need to set up a distributed tracing engine, and we want to do it all with open source tools that are available. So I chose Jaeger for that because it also has a UI that you can also search the traces, and it's really very convenient. And I think the most important thing that after we send traces from each services and see them in Jaeger, we also want to be able to trace a distributed, to see a distributed trace. This means that if in my distributed system I have two services that are communicating with each other via a queue or something like that, I want to be able to see a trace end to end.
So everything that we talked about, just implemented wise, right?
Yeah.
Perfect. That sounds cool.
Okay, let's get started. So let's talk a little bit about the distributed system that we're gonna implement. Just gonna be two small Python scripts that are both communicating via Kafka. One side is the producer that is gonna put some random messages. We're gonna give them unique IDs for each messages. And on the other side, we have the consumer that is gonna keep constantly trying to read from the Kafka. And both of them are gonna send traces to Jaeger, and hopefully we're gonna be able to see them and also see a distributed trace.
This is a classic example, though it's in Python, this is a classic example of producer-consumer schema where you're just sending message from one to another to take care for the process that you're handling.
Yeah, so first thing you wanna do is to start understand what prerequisites we have. So in terms of the application that we're gonna build, we need to install Python, install Kafka and Zookeeper. In Mac, it's easy as just brew install, or any other operating system you have. It's pretty easy nowadays to install those packages. And when it comes to installing a tracing engine, this usually what we think is going to be the hardest part, but actually Jaeger did us a big favor with coming up with the all-in-one image. I use it locally if I want to testing and like send traces right away. It's pretty easy to just use the repository, just Docker pull and use the Jaeger tracing all in one repository, and just run it. And all you need to do maybe just forward the port so you'll be able to view the traces with your browser. But other than that, it's just that easy. So let's start with building our application. Like I said, we have a producer consumer using the Apache Kafka, and the only requirement we need for that is just installing the Kafka Python library, and that's it. So let's take a look at our producer code. The producer only consists one function, which is obviously the produce one. And by instantiating the Kafka producer, I'm just using here, So in this part, I'm just using some default values. Localhost 9092 is the address of the Kafka producer, Kafka broker, and the value serializer is just the way for me to be able to encode the messages right before I send them. So just gonna be just an easier way of wrapping it instead of just doing that anytime I'm gonna send it. The producer function, all it does is just sending client to the every 5 seconds, gonna send a message with a unique ID, so we're able to identify that when we see the traces, and does it every 5 seconds. Pretty simple. In terms of the consumer, just from the other side, it does the same. It decodes the messages once it's loaded them, and just goes for each of message from the client and just prints it that it said that it received it.
Simple.
Yeah. So this code, this is just the code without the tracing. So how can we send traces from our service? What we need to do to be able to instrument both producer and both consumer. We do that using an open tracing library. Because we use the Jaeger, we're going to use the Jaeger tracing library. And we just need to do two things. First thing we need to do is to create a tracer. A tracer is an object that allows us to start new spans. A span, in our case, each span is, for example, in the producer is to produce a message, and the consumer, a span will be to consume a message. And that tracer also sends those traces to the Jaeger, and then we are able to view them. And for each operation, we're also going to create the new spans as I mentioned. So how it's going to look in terms of initiating the tracer. The configuration is pretty simple. We have a tag of a sampler, and you can configure the sampler for how many messages you want to be able to send. For example, how many percentage of each message that are being processed right now you want to send to the tracer, and just a service name. You initialize the tracer, and that's it on that side.
So just another question. What sample rate should engineers pick here? And what would the implications of that choice be in this situation?
Yeah, so this is a very good question, because when it comes to sampling, it really depends. If you have a high throttles function and you're going to send trace for each time that function is going to be executed, you might gonna overwhelm your system, and you don't want to send it. But on the other side, you want to be able to view traces end to end. So I obviously don't believe in sampling. I believe you need to send each trace, because that's the only way you can also investigate if you have any issues and see traces and not like remove them.
Yeah. So I think it's also about scaling. You've got tons of traces. Sometimes you can't store all of them, so you prefer to initially send only half of them or 10% of them. It has some limitations, because on distributed tracing you might miss something in context, but
I think that's the trade-off you need to do.
Exactly. Scaling versus
I think like rule of thumb is, if you have like very high throttle functions, and maybe need to set it to 20-30%. But other than that, it should be 100%.
Okay, thank you.
So we're gonna start instrumenting the producer. This is the only lines that I added. This is the first line is I'm gonna initiate the tracer. This is the function that I just previously saw. So we're gonna have the tracer object, and for each message we're gonna start a new span. We're gonna call it produce message. We're gonna add tags so we can later see that trace, which is the message ID, and we're just gonna send the message to the Kafka. And by using this with, once the span is closed, the tracer itself is gonna send the traces to the Jaeger itself. So let's start running the producer. Once the producer runs, it's keep posting this message. It's gonna send the message to the broker, and it's also sending the traces to our Jaeger. We're gonna try do it in live. So
live code.
Live code, yeah.
Let's hope it won't break.
Okay.
Brave.
Okay, so I'm just gonna run the tracer. It's gonna send each 5 seconds a message. You guys see that on the screen? Yes.
Yep.
Cool. So each 5 seconds, a message is gonna be sent to the Kafka. I still haven't ran the producer, so it's just gonna sit there. But what I'm looking to see from here is to see the trace being sent to Jaeger and only see the producer trace. So I'm gonna go to the Jaeger, and this is the Jaeger UI on localhost. So I can see I'm refreshing it. I can see that I have new messages of a produced message. It's really convenient. I just can go to the message and see how long it took. It took 3 seconds.
But
and,
this is not distributed since I see you're only the producer, right?
Yeah, I'll just send the producer now, and I'm gonna start sending messages from the consumer side.
Okay.
Gonna do it here. So now we're gonna run the consumer and see how it reads messages from the queue, and hopefully see that also in the Jaeger. Okay, so it's starting ingesting messages. Yeah, so now we are seeing traces both from the producer and the consumer. And I think that is very notable here that we have two different traces for a producer and consumer. And this means that when it comes to distributed tracing, we need to be able to send a correlation ID between one span to the other, and we haven't done it here yet in this example. This is why we're seeing two different traces.
So which one thinks is like the root span?
Yeah, so we don't know which is the root span here, because for us it's just like two individual traces. Mm-hmm. So this means that if the consumer is gonna fail, I won't be able to look back and understand what the producer made it. So let's go back to the
yeah.
So this is just what we saw before. We saw that each producer send a message, and the instrumentation of the consumer is pretty much the same. I just went through that and already ran the consumer, but you can see that I just started a new span with consume message, and it's pretty much the same as the producer. And just like I saw live, we have two different producer-consumer traces. And like I said, we want to be able to attach them. And the way to do that is to inject correlation IDs. So
this way, you know, on the consumer side that you're not the root span,
yeah,
but somebody else already started, and you should proceed the same ID.
Yeah. I should be able to ingest a message from the queue, and from that message to be able to extract a correlation ID, and also realize that I'm not the first span, and then I can send the span forward toward the Jaeger tracing, and then it can also attach them together.
Mm-hmm. So how we do it?
So usually it's pretty not that easy task. Jaeger gives us the ability, the tracing library gives us the ability to inject that with few, it has like few examples that you can use. For HTTP it works, I think works okay, because it puts them in the header side. When it comes to Kafka, we had to do a little thing that it calls like a custom adapter to do that. But it's not that difficult. I'm gonna show that, and also show you like a snippet of how I did it. And other than that, just it's supposed to be pretty easy. Mm-hmm. So when it comes to injecting correlation IDs, we are using the tracer inject function. You need to give it the span that you want to inject to, and what format type you want to inject. We're using a text map. A text map is just like a dictionary. And we are also going to inject it to the dictionary that we just instantiated. We called it headers, because you want to be able to inject the ID into the headers and not to the message itself. Like you said before about S3,
yeah,
that if you want to be able to move correlation ID to S3, there are no headers in S3. Right. So I don't want to, like, when it comes to S3, you need to change the file itself. I don't want to be able to change the message itself. It's not that best practice. Mm-hmm. So usually,
and this works for you?
Yeah. So this doesn't work because there's a difference between how the Kafka headers look like and how the headers that are used by the tracer itself used. The tracer uses a dictionary, and the Kafka uses a list of tuples of string and binary.
Yeah, like a nasty thing that's...
Yeah. So we just need to make like small adoption functions. I have the snippet here. You can we're gonna later see it in the presentation. You can take it from there too. So what I did, I just wrote two small functions that are gonna do the mapping. I'm just gonna move the dictionary to a list of string and bytes, and the listed string and bytes, gonna move them back into Kafka headers, so I'm able to inject and extract accordingly. So just gonna use this function along and be able to inject the correlation ID. Thanks. Yeah. Also on the consumer side, I'm gonna use that function and extract the correlation ID. And you can see here that I extracted the message from the queue, extracted the correlation ID from the queue, and then I was able to create a new span that is child of that span. So that span is being forwarded to the Jaeger tracing, and now I will be able, hopefully, to see them as one piece. So let's try to run it live. Gonna close this.
Oh, God of the demo, please be mercy on us.
It's gonna work. Okay, so I'm gonna run a deproducer. So what it does here, it's sending a message to the Kafka, but only now that it's injecting the ID that is being generated by the Jaeger itself. I'm also not responsible about the correlation ID. The Open Tracing library does it for me in terms of how it generates them. And now we're gonna run the consumer that is gonna read from the queue.
The consumer.
Cool. Okay. So we got the messages. Now we hopefully gonna see them in the Jaeger tracer. So what I'm trying to find here is a trace that has not only one span, it has two spans, and perfect. It's right here. So we have the produce message, which was the first and the origin span. So it's called produce message, and it consists of two subspans here. One is the main, which is the produce message that we can see that the message was produced, and the consume message. So this is perfect for us that if the consume message is going to fail, we are able to understand what triggered it and maybe get more information about that here.
Exactly. So we'll be able to see on the produce message the tags or our context that we have put into. And also, I think just looking at this one where you know where you spend your time in either side, this one is pretty simple because it's only two sides. But when you're having 10 services or talking to one another, so being able to know where you spend your time, this is super powerful. And with this, you can optimize and make sure and gain confidence with your application in production.
Yeah. So, I'm gonna be back to the.
Yeah, so I think it was pretty nice. I mean, we managed to cover both the theoretical side and some real practice about it. Main things that I would like to cover in our summary. So we saw that distributed tracing is crucial. I mean, it's not a buzzword anymore. It's something that if you don't have it in production, it's almost like you're blindfolded and you can't optimize your application. You don't know what's going on. Although it was pretty simple in the example that Han did, but I mean, this one very basic example in real scenario where we got tens or hundreds of microservices with lots and lots of resources. It requires a massive heavy lifting to get up and running. And as we mentioned, it's a constant maintenance. And you saw the issue where you need to translate and transform the data for Kafka for the injection. And
to be honest, I think this is like these are small issues. The more thing that you need to think of if you're gonna do it yourself or run it yourself, that that tracer need to run somewhere. So you need to have the run it on an EC2 and also maintain it. And once you go to higher scale, you need to be able to, it's not going to be that easy in terms of maintaining it and also in terms of cost, because once you go to billions of invocation or events or traces, you're going to need to have bigger a bigger tracing engine.
So you don't want to spend the engineering time on monitoring something that they should build. I mean, not building the monitoring solution, but building the right business solution. And also, I think we covered some open source tools, and like there are some things that are managed for you, that including alerts, including logs, including fully featured products that is coming out of the box for you, so you won't need to set up all of these things just to run in production with distributed tracing. One of them is obviously Epsagon, that we would love to show a really quick demo and see what is the capability when you're doing distributed tracing right and in an automated way. So first thing that I would love to show is the architecture visualization. When distributed tracing is so easy and there is a library ready for you, in this example, it's a Java library, but also Python, Node, Go, and .NET, that automatically instrument everything, automatically set the spans, automatically takes care for extracting and injecting. You can get out with this architecture with nothing. You haven't invested anything, just deploy the coder, and you can trace down every request, every performance, anything that happened. And this is just the architecture view. We promised that sometimes we need some more information or more context. So let's jump into a specific trace that is already opened. So in this example, we can see that we got a request from /order. Somebody wanted to buy one of our products. We'll be able to see what are the headers, or look just how much tracing information or context is already captured out of the box without needing to change anything. And then follow the request as it goes through any other service along the way, like an ECS cluster, where we can see some data about the cluster. We can also be able to see logs. And even in this example, there is exact example where there is a Java service on Spring Web that is sending a message to Kafka producer, and another consumer that takes care for doing something against the DynamoDB, where we can even see the items and so on, and publishing, putting an object to S3, which also triggers a Lambda function. So even on a hybrid composition of application, you'll be able to see that. So this one is visible for you, and also the timeline view, which we just shown, which is similar to Jaeger one, where you can trace down the request along every path that it went through and see each and every context payload visible for you. And everything is already stored and already captured for you, so you won't need to set up anything for that. I think that's it.
Yeah, I think the main thing that got us to build Epsagon is those things that we talked, like you don't want your team to maintain a tracing capability or monitoring capability, and we try to automate everything, so the developer is gonna invest his time only in the business logic and not waste his time on trying to run a tracer and try to maintain the tracing code.
Exactly. I think you should take the lead now.
Yeah, thank you very much for that demonstration and the theory behind that. That was really interesting. I mean, I certainly found it interesting seeing the timeline of events between the different components, and also the path visibility of the traces as well. So thank you very much. Just a quick slide here. If you are interested in container architecture, then here at Cloud Academy, we have a number of courses, learning paths, and also hands-on labs on a variety of different frameworks. So if you want to learn more about containers and microservices, then please come and take a look at our library. So, okay, I think we've probably got some time for some questions now. So let's see what's coming from everyone. Let's take a look.
We'd love to get some technical questions, please.
Yeah.
Okay, so we've got a couple of questions here. So firstly, how do you trace distributed applications in a cloud-native environment, for example, through S3, Kinesis, or SNS?
So that's a great example, and I think we briefly discussed about it, that on a Kafka, your Kafka, you can stream things however you want. But sometimes let's say in a Kinesis, it might be a bit harder because there are no headers to inject to. It's not an HTTP request. It's like something that AWS manages for you.
There's the HTTP request of AWS, but if you change the headers, you're gonna break the signature. So
exactly. And also, let's say, for example, S3. I can't change the file name or the file content because it will break things. For these specific reasons, this is one of the main reasons that we built Epsagon, because distributed tracing sometimes need to happen on the backend side. So when you're sending all these traces, something will need to fingerprint each and every event and be able to correlate between them. So for example, if you're putting a file to an S3 and some other consumer reads this file from S3, you want to be able to match these IDs without injecting it, without the inject and extract mechanism that we're having. So it's not that simple in these scenarios, and actually this is a great question.
Excellent, thank you. We've got another couple of questions here. How can I set alerts in Jaeger that when something works slow, I'll get a notification?
So out of the box, Jaeger doesn't support any kind of this thing. So Jaeger is mainly for showing traces and some sort of an architecture overview. It doesn't support any alerts. I mean, in order to get alerts, you can either build something on top of Jaeger, like a plugin or something that will work on top of that and will pull that, and you'll need to send it somewhere. So you need to integrate it into, like, I know, your Slack, your PagerDuty, your VictorOps, your Ops Genie. So out of the box, it doesn't come for you. But there are, like, an example of Epsagon or other solutions that are doing monitoring, you'll be able to find it out of the box.
Okay, thank you. Just another question from the audience. How do I differentiate between APM tools like Dynatrace and AppD, Prometheus, and Open Tracing? And are they complementary or mutually exclusive?
So there are definitely some, it's not fully complementary, but not the otherwise as well. Dynatrace and AppDynamics, AppD, are great products for APM, like application performance monitoring. Unfortunately, at the moment, they're not doing any distributed tracing, so they won't be able to show you a trace as it propagates through each and every request, which is, it's okay. I mean, not everyone is still doing it. Prometheus is more about performance monitoring of Kubernetes, so you'll be able to see all pods, all services, the memory and CPU consumption and things like that, which is also great, but it doesn't have any relation to distributed tracing. And obviously, Open Tracing is a framework, is not a solution.
It's a standard that being implemented by different things like Jaeger.
Exactly. So I think there are some things that are complementary to Epsagon or complementary to one another. I think that Prometheus can definitely live together with maybe Dynatrace or Epsagon, and as we mentioned, Open Tracing is just the API and framework. So there are some uniqueness and strengths to each and every solution.
Excellent, thank you. And we have one final question. What is the best strategy to correlate between traces and logs?
This is, I think, like the main topic that we really love to talk about, because as we saw so far with tracing, we got some context, but the real context for engineers is logs, the ability to query logs for every event that happened, the exact logs that myself as an engineer printing out, and usually I take them on Elastic or Splunk or similar solution like that. In order to correlate between them, the most simple thing that you can do once you implement a distributed tracing is to send out the trace ID, the one that we saw that propagates through the request, write it to every log line that you're writing. So every time there will be a new log line, it will have the same trace ID and even span ID. So you'll be able to see it as a story from one end to another. The better approach, if it's someone already doing that for you, so instrumenting the logs, think of logs as any general request that you're making just to write out to logs. And for example, in Epsagon, we automatically capture this kind of logs and store them as part of the trace. So then afterwards, when you're troubleshooting something, you're troubleshooting, a bad request, you also got the logs within the same trace, and you don't need to send out this from one end to another.
Okay, excellent. I think that's all the questions that have come in now. So I just want to say thank you all for joining us today, and also a special thanks to yourselves, Ran and Hen, for the discussions and demonstrations on distributed tracing. Just as a quick reminder to everyone on the call, everyone will receive the recording via an email as soon as it's available. And don't forget to check out all our other webinars, which you can find on our website here at cloudacademy.com. Thank you very much.
Thank you,
Stuart.
much.
Also, if anyone here has any question that want to ping us later, feel free to contact us. You have our Twitter handles, or you can just ping us in the Epsagon website.
Yeah, certainly. If anyone has any further questions, then definitely please do reach out.
It's been a pleasure, Stuart.
No, likewise. Thank you very much for joining us.
Thank you very much.
Thank you.
Speak to you soon. Thank you. Bye.
Bye.